All right, so if we're trying to show that the mass of the oil drop is 6.8 by 10 to the negative 15 kilograms, or given the density of the oil is 940 kilograms per cubic meter, it's helpful to sort of just write out what you're given and then let the units themselves guide your calculation. So there's 940 kilograms per cubic meter. This guides our thinking because now we know, okay, I got to cancel out per cubic meters to get just kilograms. And so cubic meter is a volume. Density rho is equal to mass per volume. And so some students would prefer to sort of start the calculation here and say, well, let me just sort of rewrite this equation like mass equals density times volume, and they would sort of begin there. Okay, well, mass is going to equal density, which I've already written down, times the volume. But without sort of formally writing it out like that, again, you can just kind of write down what you're given and then think about, okay, how do I cancel this out? Note here, the confusion of the alphabet soup that belongs with introductory physics. This M is not the same as this M, right? Like I'm solving for mass. Right? I'm trying to show that the mass M is something. This M here corresponds with meters, right? So the cubic meters, right? So just in the context of the calculation, you've got to appreciate that. So this is the density, and I got to multiply it by the volume. It's a spherical oil droplet. And what I was mentioning a moment ago to the students in class is that if you can make it as far as this, but then you say, oh, wait, I don't know what the volume of a sphere is. I need to cancel out volume. I know it's spherical. I need to know the formula for the volume of a sphere. The question isn't friendly enough to tell you what that is. So say, a spherical oil drop, where the volume of a sphere is 4/3 pi r cubed, right, where r is the radius. They just tell you what the radius is. They give you the value. They're expecting you to know that if I multiplying it by volume, right? So the way I've set this up is mass equals density times volume. So the volume is going to be 4/3 pi, and then r, and since I'm already plugging in values, I'll go ahead and type that in, cube. And so a sphere, the volume of a sphere is 4/3 pi r cubed. And if you didn't know that, you'd be at a dead end right now in the calculation, right? Like you wouldn't be able to finish it off without sort of having that formula there. If you're very confident, you might be willing to just leave the calculation like this and say, I know when I multiply all of this out, I'm going to get 6.8 by 10 to the negative 15. But that's pretty brave, right? I would encourage you to actually crunch the numbers in your calculator to actually take that value, cube it, and then note when we cube this value, we're also cubing the units, these meters. And so meters cubed are going to cancel. That's exactly what we wanted to do, to be kilograms of mass. And it is indeed true that 940 times 4 times 5 times 1.2 by 10 to the negative 6 cubed, all divided by 3, right? Don't forget to divide by the 3 down here, because the 4/3 should give you a number that's really close to that. I'm going to slide that over there. Cue up a calculator here on the screen and just kind of show that to you. So 1.2 times 10 raised to the negative 6 is that number. And once we cube it, get that. Multiply it by pi, multiply it by 4, multiply it by 940, right? So just multiplying by everything in the numerator here, and then dividing by everything in the denominator. So divided by 3, and I get a calculator value of 6.803935, as many places as you want to kind of show here. Don't forget the important part of the number, the order of magnitude, 10 to the negative 15 kilograms is about equal to 6.8 by 10 to the negative 15 kilograms, right? And so here I've sort of removed any doubt from the examiner's mind that I knew what I was doing. Like I actually calculated it to get the calculated value. I didn't just say, I know my physics, it's bound to be this because they told me it should be. If you do the calculation, you don't get what they say you should, it will reveal a mistake. Like maybe you forgot to cube it, or you forgot to divide by 3, or whatever it may be. Okay. So I encourage you to, just type it in and make sure that you show something like this. Like, yep, I've shown that the mass is indeed that based on the definition of density and the volume of a sphere. Kind of two important things you have to know to be able to do that. The question goes on to ask us to explain why a certain charge is impossible. Why would a charge be impossible? So the oil drop that we just calculated the mass for is charged. We want to explain why it's impossible for the magnitude of the charge to be 8 times 10 to the negative 20 coulombs. If you were sitting for a physics paper 2 like this, you do have the benefit of a list of formula and a list of data, including this value for elementary charge, right? So we see E equals 1.6 times 10 to the negative 19. That is the charge on an electron or a proton. It's like the minimum charge that you need. And so 8 times 10 to the negative 20 is less than that. So there's no way we could have a charge that's less than elementary charge. That's one way to explain it. Where are we at? All right. So it's impossible because this is too low of a value. Like at a minimum, we need 1.6 times 10 to the negative 19. We need elementary charge. But it is possible to have a charge that's larger than 1.6 by 10 to the negative 19 and still be impossible. Okay. And so a few weeks ago, we spelled out a procedure that you could use to solve problems like this. And so if you don't already have a nice page in your journal where you've got like, you know, this is a kind of a typical physics question, possible charges, right? So let's get a note, like how do we deal with possible charges? Is this charge even possible? Okay, how do we deal with that? Okay, start by taking the charge. Good coaching for basketball, good way to start the calculation here. Take the charge, okay? Don't be afraid. Take the charge that's given and then divide it by elementary charge. So if we take this number, any charge that you want to consider, any charge, and divide it by elementary charge, what are we looking for in our calculator to decide whether or not it's possible? Anybody remember? Take the given charge, divide it by E, and you have to know, like, so this number is less than E. So that's one way to explain it, right? Like at a minimum, it has to be this, but that doesn't immediately sort of qualify that any value greater than this is possible. That's not true. We have to take the charge, divide by this number, and in our calculator, we're looking for what to say that it's possible. Leave it down in the comments below if you know. All right, that's long enough. That's what we call adequate wait time in the teaching business. And so we're looking for whole numbers there, right? Whole numbers. And that's like saying, okay, we either have 1 electron or 2 electrons or 3. We cannot divide those fundamental particles. The concept that we link this to is that electrons are fundamental particles that cannot be divided. So if we take a certain charge and we say, oh, well, every electron has this charge, how many electrons do I got? Do I got 1, 2, 3, 4? I can't have 4.5 because there's no such thing as half an electron. And if you take this value, like this still works, even though we've already kind of explained why it's impossible. Well, it's not even the minimum value. It's less than 1. Like less than 1 isn't a whole number. Okay. 0, anyway, it's not 0. So indeed, if you were to type this in your calculator and divide it by this, you'd find that it's equal to what? 0.5. So that's a half an electron right there. That's the charge of half an electron. We don't have half an electron, right? We got at least 1, okay? So every charge in the universe must be integer multiples of elementary charge of this number. It's either 1 of those, or 2 of those, or 3, or 300, or 3 million, or 300 billion, but not 300 billion and a half. Can't have the half. So I leave it to you to kind of spell that out in your own words. The question goes on to read, the charged oil drop is in a vacuum between 2 horizontal metal plates as illustrated. Right? They tell us the strength of the field, the mass of the oil drop, the one that we just showed was that, the distance between the plates. Looks like there's a positive voltage on this top plate. This is earth or grounded. The oil drop moves vertically downwards with a constant speed. Calculate the potential difference V between the plates. So let me zoom out just a bit so maybe we can see the space to do the working and the figure at the same time. All right, so a moment ago when we dealt with density, we said that if we take care of the words will take care of us, right? Shout out to Mr. Vaughn, my high school chemistry teacher. Kilograms per cubic meter, and then we canceled out the cubic meters, right? And we had kilograms. So we can kind of do the same thing here. We know that the electric field strength is the volts per meter, and we want to calculate the volts. So if we just write down what we're given, okay, we know that the electric field is 2.1 times 10 to the negative 5 volts per meter. I need to cancel out these meters to have volts. Now that's not a negative 5, right? Come on, Schley, get it together here. That's what we call a transfer error. If you write down the wrong number, it's really tough to get the right answer, right? So it's a transfer error, but it's good to find your mistake. It's like if you do a bunch of calculations and then you look at the mark scheme or you look, at the solutions posted online or whatever, and you miss it, you want to find where you went wrong. It's like, transfer error, come on. Like that's just a careless mistake, right? And I nearly made one. So let me clean that up a bit. There we go. Still, it's not as clean. Like no transfer errors. All right, so if we know it's that many volts per meter, we just got to multiply it by the meters. So let's remind ourselves that a uniform electric field, E, is equal to both the voltage divided by the distance between the plates. And I like to show it like this, is also equal to the force per charge, right? Two things that electric field strength is equal to. If you've already previewed the calculations that are before us, we know we're going to have to solve for charge eventually. So it's usually like in the lab, we control the voltage and the distance between the plates, and so we know the field strength, but then we can use this side of the equation to figure out like the force acting on the charge, which we calculated before in this class. And then today we're going to calculate the actual charge on this oil drop, but not yet. So far, we're just calculating the voltage V. So we need to, sort of reorganize this equation, if you like to think about it like that, as well. Then the voltage is just going to be electric field strength times D. Here I've got the electric field strength E. I'm going to multiply it by the distance, if you think about it like this equation, or just canceling out the units, right? So what's the distance between the plates? I can't just write 8 mm because that won't cancel out meters, right? I've got to be able to convert that. And so what's your preference? Do you prefer to sort of write out what you're given the way that we've been doing these calculations and say, I'm just going to convert this into meters? I know that there's 1,000 millimeters per meter. So 8 divided by 1,000 would be 8 by 10 to the negative 3. Or as I've suggested in the past, if you just know that this lowercase m stands for 10 to the negative 3, and you can convert everything just like that. Say lowercase m milli means this order of magnitude. So lowercase m is 10 to the negative 3. So I have 8 times 10 to the negative 3 meters, right? And that's a way to convert it to. It's more efficient. All right, YouTube, that's your cue for a break. Okay, you've been hard at work right now going through this calculation. Go ahead and hit the pause button, get yourself a snack. We'll see you back here in just a moment. And while you're at it, don't forget to smash that like button, leave a comment down below if you've got the right answer, and get on the Dr. Schleich notification squad. We'll get new work examples out every week. All right, back to it. So we multiply this by that. We're going to cancel out the meters. We're in volts. And what do you get, class? Say it again. 1,680 volts. Good. Did you get the same thing, YouTube? Leave it down in the comments below. Now, how many people would write 1,680 on this line right here? Nobody. Good. All right. Also, a few people are like, yeah, I would. That seems pretty good to me. That's what I get on my calculator. Think about 8.0, not 8.00, but 8.0. Well, that's the same thing as 8. You know, like why that 0.0? They're saying we know it to that sort of precision, right? To that level of significance. So an even better answer than 1680 is correct. 1700, whoever thought of it. Right, rounded to 2 significant digits. This would, I'm sure, still earn both marks. Okay, because typically if you read the mark schemes for ACE physics, they'll say like within 1 significant digit, you know, earns the mark. So you can be, you know, 1 more, it really should have 2, but if you put 3, you know, they'll typically give you the mark. But before, remember, we had a number that was like 6.8039. There was a lot of digits there. You would not want to report it to like 5 or 6 or 7 decimal places if the numbers that went into the calculation were only reported to 2 significant digits. So the precision that goes into the calculation sort of comes out as the general rule. All right, the question goes on to ask us to explain how the motion of the oil drop shows that it is in equilibrium. And so using this question as a problem study, we can remind ourselves of the conditions for equilibrium. So students of physics will know that something is in equilibrium if there is no net force acting on it, and there is no net torque or no net moment. Now, this question isn't about torque at all, right? There's no force applied a distance from a pivot. So really, it's the first criterion that we're considering. If there is no net force, right, then it's in equilibrium. Well, how can we explain how this thing has no net force acting on it? The motion of the oil drop. Here they say the oil drop moves. How does it move? It moves vertically downwards, okay, but with a constant speed. That's the key right there. If something has constant speed, is it changing its velocity? Well, the rate of change of velocity is acceleration. And if something has constant speed, it's not changing its velocity, right? That's what constant means. It's the same speed. So if it's not changing its velocity, something with constant speed has what value of acceleration then? Exactly, nothing. You don't have to say anything, 0. So if the acceleration is 0, and we say, well, the sum of the forces, the net force, the resultant force, is equal to mass times acceleration. And if something isn't accelerating because it's moving at constant speed, then we can deduce that the forces must be balanced, or the resultant force is 0, or there is no net force. Yeah, we did that. So you want to kind of put all those ideas, you know, in your own words with a nice complete sentence that reads something like, because the oil drop moves with constant speed, the acceleration is 0. Because the acceleration is 0, the forces are balanced, and therefore there's no net force, showing that it's in equilibrium. Something like that. You know, there's lots of correct ways to state that are perhaps more concisely worded than I just said. But there's a natural syllogism there, right? A logic that goes, oh, because this is true, if that's true, we can say this. So it's a quick recap. Constant speed means no acceleration. No acceleration means the net force is 0. And that's the exact condition we're looking for to show equilibrium. Over. Determine the charge on the oil drop. All right, let's keep in mind that we need to both calculate the charge and the sign of the charge. Let's go back up to figure 4.1 to consider that. All right, if this is the positive plate and it's on top, we can draw some field lines, right? There's an electric field, a uniform electric field. What direction does the electric field point? Using this as a review, we can say, oh yeah, there was a rule that we talked about for the direction of an electric field. It's how does a proton move? How does a positive charge move? And so if you put a positive charge in the middle of this, it would be repelled by the positive plate on top, right? So it's gonna move this way. If a proton moves down, then how would, and again, if this thing were positively charged also, then it would also have a downward force and it would be accelerating in that direction. And so we can immediately deduce that the charge on this oil drop is negative because the electric force is acting upwards, opposite the direction of the electric field. Right? The electric field pushes a proton down or a positive charge down. So how do I know the electric field is pushing it upwards? Well, we just said that this thing moves with constant speed, that the forces add up to 0. And we said that this is an oil drop that has mass. Okay, if something has mass, what else can we say it has? To say it has mass is to say it has somebody give me the alley-oop here so I can slam dunk here. If something has mass, it has. Wait for what? I want to answer. Ha ha ha! Resounding laughter throughout the classroom. Don't worry, I'll edit it later. But yeah, that's the bad joke, right? Wait. All right, wait for what? I want to answer. So yes, if it has mass, it has weight. You can imagine that this apparatus is on Earth, okay, where we know the gravity field strength. So there is a force acting down called weight, and if it's not accelerating downward, that must mean that there's an up force, right, pushing it up here. So if we're trying to calculate the charge, we know that the uniform electric field is equal to voltage divided by distance, and we know what that value is. We know it's equal to force per charge. And so again, some students prefer to just like, let me start with the equation that's going to solve it. If I want to solve for the charge, let me just write that Q is going to equal F over E, right? That's just reorganizing this equation for electric field. But while we know the electric field strength, it's given, what is the force acting on it? You can't say, oh, we just said that there's no net force. The force is 0. You have to consider this as, this is the electric force. This is this force that's pushing it up. And how do we know what it is? What we know is that it's equal to weight, and we know how to calculate weight. Okay, so you can really just say, okay, well, computationally, my numerator here is just the weight mg. But you have to connect the ideas here that this is calculable, and we know that it's equal to the electric force. The force in this equation is the electric force. Okay, it happens to be equal to weight, so we can calculate it with mg. Okay, so it's going to be mg over E to give you Q. Mg over E. I'm going to do my working right here. Nice space for that. All right, so let's see how well we can remember all that. We said that Q was going to be F over E, and it is the electric force, but we know with a little sort of free body diagram, we got the oil drop with weight, and it's got a balanced electric force here. So that electric force is the same as mg. Mg over E solves for the charge Q. We already know the sign was negative, right? We already talked our way through that. We said, okay, this got to be a negatively charged thing for the force to be pointing against the direction of the electric field. The mass was 6.8 by 10 to the negative 15 kilograms. You can assume this is happening on Earth, where G is 9.81 newtons per kilogram. So there's what will cancel out the kilograms. And remember that an electric field could be thought of as volts per meter, but also newtons per coulomb, right? A newton per coulomb is like this, force per charge, right? So a volt per meter is the same thing as a newton per coulomb. So here the newtons are going to cancel, the kilograms are going to cancel. We're left with the unit we should be in, right? The coulombs. And if you multiply those two numbers and then divide by that, what number do you get? All right, YouTube. Don't be so lazy that you're just letting me type it here on the screen. Get out your calculator and let's follow along together. If you're in class, that's fine. You'll just be lazy. It's like, oh, we'll let you, we can see it up there on the projector. But YouTube, I'm counting on you to get that calculator out. What do you mean it's out of batteries? It's not solar powered? What are you doing? Divided by open parentheses, right? You're dividing by something in scientific notation. Got to use grouping symbols. Order of operations. Now, I do get a calculator value. That is there. 3.17657 by 10 to the negative 19. Is that possible, right? We just looked at this idea of like possible charges, and we also talked about significance, right? And so we say, okay, well, I should really, I heard, I think Holden say it, 3.2 by 10 to the negative 19. Okay, 3.2 by 10 to the negative 19. And then you could use that procedure that we spelled out a moment ago and say, let me take this charge here, divide by elementary charge, and realize that's exactly 2 electrons. Right? You can see like, oh, if I divided this by 1.6 by 10 to the negative 19, it equals, my calculator will show the number 2. That's telling you I've got 2 elementary charges, 2 electrons. So that oil drop is in a uniform electric field, and the electrons, there's a net of 2 electrons, 2 excess electrons deposited on the surface of that oil drop, giving it just enough force in that electric field so that it just moves down at constant speed, showing that it's in equilibrium. But what's going to happen, you're probably wondering, if we decrease the potential difference between the plates? Okay, the magnitude of the potential difference between the plates is decreased. Explain why the oil drop accelerates downwards. So we want to anchor our thoughts to equations in physics typically. If the magnitude of the potential difference, the voltage, right? Potential difference is the voltage. If that goes down and we don't change the distance between the plates, right? Then the electric field is going to also go down, right? It's going to become less strong. Well, remember, the electric field was the thing providing the electric force that was balancing the weight. And so if you decrease the electric field strength, you're also decreasing the force that charge is experiencing, right? This is the region of space where a charge experiences a force. So you want to kind of put that in your own words now, right? Turn the question around, right? So turn the prompt around. So, how do I start wording this? The oil drop accelerates downwards because, so if we're trying to explain why, so we want to kind of use that. So the oil drop accelerates downwards because the electric force decreases. Right? Or you could say the electric field becomes weaker, so there's less force, electric force acting up on the particle. No longer is it going to be true where the electric force equals weight. Okay, we haven't changed the weight vector. It still is 6.8 by 10 to the negative 15 kilograms of mass. It's still in Earth's gravity field. So if you make this weaker, I'm trying to exaggerate how much weaker it is than this, there's going to be what? A net force downward. And whatever the direction, there's a net force, a resultant force is the direction of acceleration. So you could say things like, the weight is greater than the electric force because the electric force is weaker due to the electric field becoming weaker with decreased voltage, right? So again, it's always about connecting those ideas. There's 2 marks there, and you kind of want to just think your way through that, right? Because the voltage goes down, the electric field strength goes down, which means there's less force. The lower electric force no longer balances the weight, or it is less than the magnitude of the weight vector. Therefore, there is a net force downward causing the oil drop to accelerate down. Right, so lots of different ways to sort of state that. One of the best things that you can do as a scholar, as somebody studying not just physics but in any subject, is to try to sort of go back through it and put it in your own words and see what kind of sense you're able to make of it. When you close your notebook, it's like, okay, what was important about that? Right? So, non-cued retrieval practice is what a lot of research shows to be one of the strongest study skills that students can utilize. All right, moving right along, it says, describe the change to the pattern of the field lines, the lines of force representing the uniform electric field as the potential difference decreases. So I had previously drawn some field lines on figure 4.1 here. And the rule is that sort of like the density of the field lines shows the strength of the field. So if before, there were field lines like this, and this is how I'm representing this strength, then I draw less, lines, or there'd be more space between them. So you're trying to, I guess, just put that into words. What happens to the pattern of the field lines? They get further apart. There's more space between them, right? The change to the pattern of field lines representing the electric field as it decreases. So because the field is getting weaker, there'd just be fewer lines or more space between the lines, however you want to sort of state that. Instead of having something like, in a uniform field, they should be about equally spaced. So instead of saying we have something like that, you have something like that. Right? You kind of want to, and don't draw a picture like that and let that stand as your answer. Okay, you really do need to describe with words what we're trying to show there. So however you would describe that, there's more space between them or there's fewer lines. They're both correct. And now the fun puzzle, part D. So this goes back to chapter 3. This is types of forces. And it is a little puzzle there. They say there's two types of force, X and Y, and they can act on the oil drop when it is in air, but cannot act on it when it is in vacuum. We had just been considering the oil drop in a vacuum, so we only had to consider two forces, right? Weight and electric force. We only had to consider those two because it was in a uniform electric field and it was in a uniform gravity field. You may recall doing our quizzes a few weeks ago where we had to consider both of these forces, right, for a very similar question. You may recall the essential question about Millikan's oil drop experiment. You say, oh yeah, that's kind of what we're doing now, right? Working a little bit with that kind of experimental apparatus. So we didn't have to consider any other forces besides these two. But now, okay, we're in air. So forces that act on it when it's in air, but they do not act on it when it's in a vacuum. So we didn't have to consider them previously. Force X can act on it when it is stationary or when it's moving. Force Y can only act on the oil droplet when it is moving. Okay, so both of the forces act on it in air, but not in vacuum. Force X acts on it either moving or stationary. Force Y only acts on it when it's moving. And we have to state the name of those forces, X and Y. See how it's a fun puzzle you get to solve? You guys are so lucky. You get to solve fun puzzle physics questions. Or all I ever got to do was like boring stuff with physics. Just kidding. It's all boring. No, it's all awesome. Anybody know any forces that act in air? Now you might be thinking, hey, we've done something like this before. We were studying the physics of skydiving. We had to consider two forces, but they weren't weight and electric forces, right? We don't go skydiving in an electric field, although that would be pretty awesome. Think about it. You have like a charged suit, jump into a uniform electric field. They have kind of places like that. Well, it's not like electric fields, but they have like, indoor skydiving, right? Where they use like a fan, So what force is that? When you jump out of an airplane, you got your weight accelerating you downward, but you crash into enough air, and what's going to affect you when you're moving through air? Drag. So the force, it is a resistive force. It's a type of friction. We call it drag. That's got to be the one when it's moving, right? You have to be crashing into air for drag to affect you. You're in air right now, and it's exerting a pressure force on you. If you run really fast, eventually you'll run so fast that the air that you're crashing into will equal the accelerated force of your feet propelling you forward, and you'll be at a top speed. Or if you ride your bicycle very fast. Like you can reach terminal velocity in a bike going horizontally, just like you can falling vertically through air as a skydive. So we know that force Y down here must be drag. Okay. Force Y is drag. Does anybody know a force that also acts, you know, in air when it's moving, but it can also act on it when it's stationary too? So this is the force called upthrust. And it's basically why things float. Okay, so there is more pressure, so like underneath a hot air balloon than there is above it. So there's a net upthrust. Okay, so it's going to float. A boat that's floating in the ocean, okay, has an upthrust force that's pushing it up, right? Because we know that a boat has weight that would otherwise make it sink. So why doesn't the boat sink? It goes back to the idea of conditions for equilibrium. There's no net force. If there's a down force weight, we're always looking for the up force that's balancing it. Thankfully, you know, the cruise ships out of the port, they don't sink, right? They are built in such a way that their density is lower than water. And so there's a net, there's an upthrust force equal to the weight. And it's a lot of weight, right? Like those cruise ships are massive, lots of stuff, lots of mass, right? So lots of weight, but they're built in such a way that upthrust equals the weight. Okay, so they're in equilibrium. There are questions, and you'll find them if you scour, you know, paper 2, that will ask you to explain the source of upthrust. So you want to be able to kind of keep a picture of moving molecules in mind and think about how, you know, the further down or sort of like the deeper down in the ocean you go, there's going to be more water molecules down there. And those water molecules are going to crash into the bottom surface, you know, of the boat more than the fewer molecules sort of at the top, right? And so when water molecules, you know, crash into the surface of something, we got this sort of basic physics that we've studied before, right? A mass crashes into a wall and it changes its direction. Well, it's changing its momentum, right? So if it changes its direction, even if it goes at the same speed, even if it's a perfectly elastic collision that those water molecules or those air molecules make with the surface, there's going to be a change in momentum because the direction changes. And we know that the rate of change of momentum is force. Okay, so there's going to be more force on the bottom side of something than there is on the top, and that's what upthrust is. A force that can act on the oil drop, both when it's stationary, because there's air on the oil drop when it's stationary, also when it's moving. So if you did this experiment not in a vacuum, you also have to contend with those other forces. You have to deal with the fact that the air, even when it's not moving, the air is crashing into it. Okay, a little bit more on the bottom than on the top. Now the radius was like a micrometer, so it probably wouldn't be that big of a difference. But for something like a cruise ship, you know, which is sort of bigger in size, right? That sort of difference in pressure is more pronounced. All right, 14 marks on this one. Very lengthy paper 2, but a nice problem study.